Greetings! Welcome to Electronic Circuits 1. I am Razavi and this is lecture number 41. Today we will look at the third type of amplifier topology in CMOS technology, which we call the source follower, also known as the common drain topology. And we will see what properties it has and how it helps us with circuit design. Before we go there, let's refresh our memory about what we covered last time. We were looking at the common gate stage as the second type of amplifier design in CMOS. And we saw that in this case the input is applied to the source of the transistor and the output is taken from the drain of the transistor. And we saw that in this topology, if we neglect channel length modulation, the voltage gain is given by Gm times Rd. Very simple and without a negative sign. Sorry, I think I have made a mistake here. This should be plus. Okay, and then we also found the input and output impedances of the circuit. And we saw that the input impedance is about 1 over Gm. We say looking into the input, we see 1 over Gm. And it's a relatively low value. And we saw that perhaps it could be used to match the impedance of an antenna, as an example. And the output impedance, if lambda equals 0, is equal to Rd. Well, that's something to remember. The input and output impedances become important when we interface the circuit with other circuits preceding it or following it. Then we looked at the biasing of the common gate stage, and we saw that we needed some sort of voltage at the gate. So instead of a battery, we use a resistive divider, similar to what we did for the common source stage. And then we saw that we still need a path from VDD through the load resistor, through the MOSFET, to ground to carry the drain bias current of the transistor. So we have to have some two-terminal device here that allows the DC current to pass. It could be a resistor or an inductor or a current source. And in the simplest case, we chose a resistor for this biasing. So it's important to remember that we need a path for the bias current. It has to go through this, or it has to go through the preceding device or stage, if that's possible. All right, so today we will move to the third type of amplifier design and repeat that type of analysis. Namely, we will look at the small signal behavior and the biasing techniques for the source follower. So let's see what source follower means. So let's look at the source follower topology. In this case, we have the input coming to the base of the transistor, the gate of the transistor. So we say input applied to gate. And the output is taken from the source of the transistor. So we say output sensed at source. Okay, so it's a little different from the previous stages. The input is applied to the gate, the output is sensed at the source. All right, well, the way I have shown this circuit, it won't work because we need a bias current in the device. The bias current has to start from the positive power supply VDD and flow this way all the way to ground. So we need a DC path from VDD to ground. So again, like the common gate stage, we need to connect something between here and here that allows a bias current to flow. So in the simplest case, we use a resistor for that purpose. So we connect a resistor here, we call it RS. So that is a relatively complete common source follower, also known as a common drain amplifier. Okay, so we would like to analyze the small signal properties of the circuit, including the voltage gain, the input impedance, and the output impedance. For the voltage gain, we can have a quick and qualitative look first before we jump in and write the equations. So let's do this. Remember what we did for the common gate stage. Let's apply a small change to the input. So this input has some bias value. If you remember, we always have some sort of battery or something here. And then on top of that, I apply a small step. So here's a small step of delta V. And I would like to see what happens at the output, just qualitatively speaking. All right, well, the output has three possibilities. It goes up, it goes down, or it doesn't change. Now, it had better change because, after all, this would not be an amplifier or a useful circuit if the output doesn't change. All right, but let's assume that the output does not change and proceed and see what type of contradiction we face. Okay, so if the output doesn't change, it means that this current doesn't change. Voltage divided by resistance has to be constant. All right, so we're saying that the output is not changing, this current is not changing. Now, if the output, meaning the source voltage, is not changing, but the gate voltage is going up, the VGS of this device is increasing, which means the drain current has to increase. But that drain current has to flow through RS. So the current through RS has to increase. And that contradicts the assumption that V out is constant. That means that V out must also go up by some amount, which we don't know yet. So V out has to go up. So that's the only conclusion we can draw. And you can see that this analysis is similar to what we did for the common source stage with degeneration, when we were looking at the source voltage and see how it goes up and down. All right, so what we see for the source follower is that when the input goes up, the output also goes up. Obviously, when the input goes down, the output also goes down. In other words, the source voltage follows the gate voltage, and that's why it's called a source follower. It's a strange name, but that's how it came about. All right, so now we can go ahead and draw the small signal model of the circuit and find its small signal gain. For now, we will assume that lambda is equal to 0. All right, so let's go ahead and do that. For the input, we have an AC voltage source. So that's V in, small signal voltage source applied to the input from this point to ground. Then we draw the model of the transistor. By now, we should be comfortable doing this. GMV1, V1 is between the gate and the source. Then we have a resistor connected to ground, RS. The output voltage is here with respect to ground. So the output voltage measured between here and ground. And then the top of the current source goes to AC ground. So that goes to AC ground. As usual, we would like to eliminate V1 and find V out over V in. Okay, well, that shouldn't be that hard. Let's write a KVL around this loop. What we see is that we have V in. This voltage is equal to this voltage plus this voltage. And this voltage happens to be V out. So we have V in is equal to V1 plus V out. Okay, that says that V1 is equal to V in minus V out. Now, let's write a KCL at this node. This current is coming in is equal to GMV1, and we have V1. And the current through RS going downward is equal to V out over R1. So I can say GM times V1, V in minus V out, is equal to this voltage over this resistance, V out over RS. So now we can find V out over V in. So we have V out over V in is equal to, one way of writing it is RS, 1 over GM plus RS. We can also write it like GM RS over 1 plus GMRS. Both of these are common forms. Whichever you like, you can choose. Not a big deal. We can always go from one to the other. I usually remember it this way because, again, I can verbalize this result. Okay, so let's try to put this in words so that we always remember it. So we say that for a source follower, the voltage gain is equal to the total resistance tied between the source and AC ground from here to here. That's in the numerator. So resistance tied between source and ground. Ground means all grounds. So that goes in the numerator. In the denominator, we have the same value plus 1 over Gm. So we can say 1 over Gm plus the resistance tied between source and ground. So that's a good way of memorizing the voltage gain of a source follower. Regardless of how complex these values could be, we can always use that equation to write the voltage gain quickly. Okay, all right. Now, if you look at this carefully, we see that this voltage gain is always less than 1, depending on the values of RS and 1 over Gm. The best we can do is try to make RS very large, much greater than 1 over Gm, so that this voltage gain approaches 1. But that's the best we can do. So the voltage gain of a source follower is always less than 1, which begs the question, why do we want to use a source follower? It seems that a circuit with a gain of less than 1 would not be very useful. Why don't we just use a piece of wire instead of this whole circuit here? So we'll get there in a minute. All right, the next parameter that we want to calculate is the okay, so let me show you another way of deriving this result, which is also very nice and intuitive. It helps us greatly understand what a source follower is. So this is an alternative technique of analyzing the source follower. So let me write here alternative analysis. All right, so let's do this. Rather than go through the small signal analysis and write all these equations, maybe we can use some of our knowledge from Circuits 101, namely Thevenin equivalent, Norton equivalent, that sort of thing, right? So maybe what I can do is this. I have the circuit, and I'm too lazy to write these equations. So I'm thinking maybe I can represent part of the circuit by a Thevenin equivalent, which hopefully is easier to analyze, and then connect everything together. In other words, what I'm thinking is it possible to represent all of this by a Thevenin equivalent and calculate everything, the Thevenin voltage, the Thevenin resistance, and then connect the result to this resistor and see what Vout I get? This is just a simple exploratory question, and maybe it has some interesting results. All right, now you know that the Thevenin equivalent is possible only if this part of a circuit and this part of a circuit are connected by exactly 2 wires, no more, no fewer. So you can see that this circuit and this circuit are connected by this wire here and this wire here. This ground goes to these grounds. There's nothing else. You cannot have, for example, a dependent source here which depends on some value inside this box, or vice versa. That does not allow us to write a Thevenin equivalent like this. But here the situation is very simple. I just have this box, and I would like to find its Thevenin equivalent. Okay, so now let's go back to Circuits 101 and see how we calculate the Thevenin equivalent of the circuit. So let me write here Thevenin equivalent. And this is the circuit of interest to us. We have some very strange but simple circuit. Here's what we have. We have a voltage source inside, which we call V in. Then there's a dependent source, like so. And this is the output node, right? You want to find the Thevenin of the circuit here. Okay, well, Thevenin says, in order to find the Thevenin voltage, all you need to do is disconnect the box of interest from the rest of the world and find the voltage at this output. This is what we call the open circuit voltage, meaning that it is not connected to the rest of the world. So let's go and find this voltage without RS present. So we'll call this V Thevenin. And we'd like to see how much that is. Now, again, I'm hoping that these calculations are simpler than this algebra here. Okay, how much is V Thevenin? Well, what we see is that GMV1 has nowhere to go, right? Because that's what Thevenin said. You have to disconnect this from the rest of the world, so there's no current going that way. If GM1 has nowhere to go, GM1 has to be 0. And that's only possible if V1 is 0. If V1 is 0, then how is V Thevenin related to Vn? They are equal, because if you write the KVL, you see this voltage is equal to this voltage plus this voltage. V1 is 0, so V Thevenin is equal to Vn. So we'll write this for now. We say that GMV1 has to be 0, which means V1 has to be 0, which means V Thevenin has to be equal to Vn. So that's nice and quick, right? We don't really need to write much algebra. Okay, in the next step, we have to find the Thevenin resistance. And we know how to do that. Thevenin says, kill all the independent sources inside the box, and then come from outside and apply a small signal voltage Vx, measure the resulting current Ix, and that ratio will give us the Thevenin resistance. So let's do that. We'll kill the source. That will give us something like this. V1, GMV1. This is AC ground. This is the box without independent sources. And now we apply Vx and measure Ix. So what does that tell us? Well, this is very simple. We see that Vx and V1 are related. We've seen this a number of times. Here is Vx and V1 are negative of each other because they go from this node to ground, right? So in this case, we see that Vx is equal to minus V1. That means that this current is equal to minus GMVx. All right, so let's write the KCL here. Minus GMVx plus Ix must be 0. So minus GMVx plus Ix must be 0, which means Vx over Ix is equal to 1 over Gm. So the Thevenin resistance of this structure inside this box is 1 over Gm. All right. Is that very surprising that this is 1 over Gm? Do you remember 1 over Gm from the past? What impedance was equal to 1 over Gm in the past? Well, there were two cases. One was a diode-connected device without channel length modulation. Is this a diode-connected device? Yes. You see, the gate and the drain are both shorted to ground. So it is a diode-connected device, even though when we started out it didn't look like that, right? But in the small signal model, it is exactly like a diode-connected device. And the resemblance between this and the common gate stage input impedance is also not coincidental and follows the same type of thought process. But anyway, let's continue. Okay, so we have constructed Thevenin equivalent. So let's do that. We have, for that box, we have V in, because we decided that the Thevenin voltage is just V in, and then the resistance, which is 1 over Gm. This is the box. This is the Thevenin equivalent of this whole thing. Now we go ahead and connect it to RS and see what we get. So we connect it to RS, and of course this is a simple voltage divider, so V out over V in is equal to RS divided by RS plus 1 over Gm, which is what we had before. So this alternative analysis tells us that a source follower without RS is just an amplifier with an output resistance or internal resistance, if you like, of 1 over Gm. And the fact that we connected RS to it, because we wanted to have a bias current, reduced the gain to this value. If we had not connected RS, or if RS were extremely large, we would not have attenuation from here to here, and the voltage gain from here to here would have been 1. But RS might not be very, very large, and as a result, we get some attenuation. So that's a very nice way of thinking about the source followers. All right. Now that we have done this quick analysis, we can also try to gain more intuition if we assume lambda is not 0. We will try and see how it goes, right? Sometimes it's too complex, sometimes it's not. In this case, it's not that complex. So let's assume lambda is not 0 and see if the analysis can be repeated quickly. All right, well, I go back to that equation on top, and I see if I can apply that equation when lambda is not 0. So let's go back here and ask ourselves, with channel length modulation included, we have RO from here to here, right? Between the drain and the source. So that would be where? That would be here, between the drain and the source. Between the drain and the source. And the drain is grounded. So it's between the ground and the source. Between the ground and the source. Right here. So RO is actually in parallel with RS, as you can see. Again, it might be easier to see here too. We have RO going from here to AC ground, and RS going from here to AC ground. So they're just in parallel. Okay, so wherever I have RS, I replace it with RS in parallel with RO. Because we have the resistance tie between source and ground. Now, it's not just RS, it's RS in parallel with RO. And similarly in the denominator. So we say AV is equal to RS in parallel with RO, RS in parallel with RO, plus 1 over Gm. So that's very easy, right? We could include that readily. I can also go back to this business here and notice, again, the same situation, that RO is connected from the source to ground, so it gives me the same result. Now R1, RS in parallel, so we have an attenuator consisting of RO in parallel with RS, and then divided by RO in parallel with RS plus 1 over Gm. So it's the same result. Okay, so that was for the voltage gain. We still don't know what good an amplifier with the gain of less than 1 will do, but don't worry, we'll get there. Let's try to find the input and output impedance as well. Okay, so Rin doesn't need much thought. Looking into here, we see a very high impedance because the gate doesn't draw much current. So we'll say Rin is equal to infinity at low frequencies before the capacitances of the device come into the picture. How about the output impedance? For the output impedance, we have to kill all dependent sources. So we set this to 0, that to 0. we apply something from outside here and measure the resulting current. So let's do that. We can do that here, we can do that here, or we can even do it here. And all of these give us the same result. So maybe we'll do it here. That's nice and simple. So let me draw this circuit with the input source set to 0, and then apply something from outside trying to measure the output resistance. Okay, so here's how it goes. We have 1 over Gm. The input is set to 0. Then if you want to include RO, no problem, we can still include RO. And then we have RS, and then we come and apply Vx and measure Ix. So now we see that 1 over Gm goes in parallel with these two. So the output impedance is very simple. We say, sitting here and looking into the output, I see 3 resistances going to AC ground. One, from the intrinsic transistor. Looking at the source of the transistor, we see 1 over Gm. That was similar to looking into the input of a common gate stage, right? Or a diode connected stage. Doesn't matter because this point is AC ground. So looking into here, we see 1 over Gm. Looking into here, we see RO. Looking into here, we see RS, all 3 in parallel. So we say R out is equal to 1 over Gm in parallel with RS in parallel with RO. All right. So that's a nice way of analyzing the source follower. One note of caution, when I analyzed the circuit like this and I got to here, I had not included channel length modulation. And for RO, I just dropped it outside this box. That's fine. Alternatively, you can go back and keep RO inside this box and find a new Thevenin equivalent in terms of the voltage and in terms of the resistance. And that's fine too. Okay, so either way works. You can keep RO outside that box because it is really outside. It's just tied between here and AC ground. That box is just the MOSFET itself. Or you can keep it inside the box and have a new Thevenin equivalent, and these results will remain intact. Very well. Now that we have seen these, we can make a quick observation. The voltage gain of the source follower is less than 1. The output impedance of the source follower is relatively low. 1 over Gm in parallel with some other resistances, probably 1 over Gm dominates. It's a small resistance compared to these two values, typically, hopefully. So we can say that the output resistance is relatively low. So the source follower is very interesting. It has a high input impedance and a low output impedance, sort of the other way from the common gate stage. And we have to see how we can utilize an amplifier that has a gain of less than 1, but has a high input impedance and a relatively low output impedance. So for that, I'll show you an example, and we'll see how these come into the picture. All right, so let's go add a page. Okay, so this is the application, one application of the source follower. All right, so let's say we have designed a common source amplifier with some gain. So here's a common source amplifier. And as an example, I have chosen 500 ohms for the drain resistance. And then I chose the dimensions and bias current of this guy to give me a GM of, let's say, 1 over 40 ohms. So GM is 1 over 40 ohms. Okay? And again, lambda is 0 for simplicity. All right, so we see that this amplifier by itself provides a voltage gain of GM times 500. So the voltage gain is equal to minus 12.5. That's quite respectable. All right. Now, this amplifier is amplifying and then eventually has to drive something, right? You can't use it by itself. This node has to go somewhere. And let's suppose that I'm using this amplifier at the output of my Bluetooth transmitter. So let me take you back to the Bluetooth transmitter and refresh your memory as to how this worked. So here's what we had, if you remember. We said that we apply our pulses to an oscillator so as to modulate its frequency. And then this output needs to drive an antenna. We need a power amplifier between the oscillator and the antenna so that it can deliver a high power to the antenna. We want to have a high power transmission so that the range between the transmitter and the receiver is maximized, the distance. Okay, so this power amplifier, in its simplest case, might be just a common source stage. So I designed the common source stage, where, as you can see, with a gain of 12.5. So I'm happy with that. But now I go ahead and connect it to the antenna. And the antenna has an impedance of 50 ohms. All right. So now we go and connect this to an antenna. And this antenna has an impedance of 50 ohms. You can model that by just a resistor to AC ground. Okay, so this is equivalent to a resistor to AC ground. So do we have a problem? You can see that the total resistance tied between the drain and AC ground consists of 500 ohms in parallel with 50 ohms. So you can see how disastrous the situation is. So let's write the new AV is equal to minus GM, so minus 1 over 40 ohms, times the total resistance tied between drain and AC ground, 550 in parallel. So 500 ohms in parallel with 50 ohms. And this gives us a gain of how much? Get a gain of 1.14. All right, so the gain plummeted as a result of the connection to the antenna. Okay, so what do we do? Well, we can try to play with this circuit itself and maximize the gain. You know, we can try to push GM as much as we can. But a better approach, perhaps, is to try to place what we call a buffer between the stage and this load. This load is considered heavy, meaning that its value is low. It wants a lot of current. So we can try to place some buffer stage between these two. And the source follower would be a good buffer in this case. A buffer is a stage that tries to not load this guy so much, meaning that it wants to keep the gain of this circuit intact, and yet be able to drive this load with some moderate gain or some moderate attenuation. So let me draw this and see, I'll show you what happens. All right, so we have the common drain stage as before. Here's RD, 500 ohms, and we come out here. The same transistor as before, so GM is about 1 over 40 ohms. And now the load, which is a 50 ohm resistor to AC ground, is driven not by this directly, but by a source follower. So we call this M1, this M2, and this is V in, and this is V out. And this is the antenna. Okay, let's assume the same GM for M2 as well, just for simplicity. So GM2 is also 1 over 40 ohms. And we are curious to see how much voltage gain we get now. Without all of this, we got 12.5. With directly driving the antenna, we got 1.14. With this buffer stage, do we get something reasonable? Okay, so that's not that hard. We just say, again, we call this node X, and we say the small signal voltage gain from the input to the output is equal to Vx over Vin times V out over Vx. Vx over Vin is the same as the old case, because looking to this gate, we see a very high impedance. This gate doesn't draw much signal current, so the gain of the first stage is approximately the same as before. So we have minus 12.5 here. That's good. Then that's multiplied by the gain from here to here. That's the gain of a source follower. And we know how to do that. The gain of a source follower is given by the total resistance tied between the source and AC ground, 50 ohms, divided by that resistance plus 1 over Gm of that transistor, so 40 ohms. So multiply these, and what we get is minus 6.9. So it's not too bad. It's much better than this voltage gain that we got when we try to drive the antenna directly. So this is an example of how a source follower serves as a buffer, and really this is the only application of source followers, good buffers or moderate buffers in many cases where we have to drive a heavy load. So this shows that we could do this in case the common source stage itself has difficulty driving 50 ohms. Okay, very well. Let's talk a little about let me give you one more example of usage of source followers, and just for analysis purposes, let me change the color of my pen. We'll look at a circuit and we'd like to find its voltage gain, just for fun of it. So here's a source follower, and then we drive a common gate stage by that source follower. And if you want, you can connect a battery here. We know that these all have to be biased properly. And V out is here. We have RD, RS, M1, and M2. And this is the input. So we need to find the voltage gain of the circuit. It's a cascade of stages. It's a cascade of a source follower and a common gate stage. So as usual, we will call this node X, and we'll say V out over V in for small signal quantities is equal to Vx over V in times V out over Vx. All right, so let's write it out and see what we get. So the total voltage gain is equal to Vx over V in. That is the voltage gain of the source follower M1. And we said that the voltage gain is given by the total resistance tied between the source and AC ground divided by that plus 1 over Gm. So how much is the total resistance tied between the source and AC ground? Okay, well, we have RS going to ground, so we keep that. Do we have anything else going from X to AC ground? Well, yes, because this terminal draws AC current, right? Do we remember that looking into the input of a common gate stage, we see 1 over Gm. So this is 1 over Gm2, assuming, of course, that lambda is 0. So at node X, we have two impedances going to ground. One is RS, and one is 1 over GM2. So these two are in parallel. You have to place them in parallel. 1 over GM2. That is the total resistance tied between the source and AC ground. So we copy that in the denominator, 1 over GM2, and then add to it 1 over GM of the source follower transistor. So 1 over GM1. This expression is Vx over Vin. Now we need to find V out over Vx. But that's just a simple common gate stage. We know its voltage gain is given by Gm times Rd if lambda is 0. So that's just Gm2 times Rd. So that was easy enough. Again, we would like to take a relatively complex circuit, break it down into pieces that we know very well, and use the analysis like so, rather than draw the small signal model of everything and write n equations and unknowns. Okay, in the next step we will go to the biasing problem for source followers. So let's look at bias design and see what we have to do. All right, well, we decided to use a resistor in the source follower to provide a path for the current to flow from the power supply all the way through the transistor and through the resistor to ground. So that was the reason for using RS. Otherwise, we prefer to have no RS, right? If we had infinite RS, the gain would be 1, approximately, if channel length modulation is neglected. But we have to have RS. We have to have something. It could be a resistor, it could be a current source, something. It has to be there. Okay, but how about the gate? What do we do with the gate? The gate also needs some sort of voltage in the absence of signals to make sure that we have proper VGS and all that, and we have a current, etc. So, well, maybe what we can do is connect the gate to VDD. Is the transistor biased properly in this case? Looks like it. We see that the gate is at VDD, so some voltage, 1.5 volts, 2 volts or something. Then we have some VGS, then we have a resistor here. So this is actually similar to the common gate stage we analyzed last time. So we have some VGS here, some drop here, we can have some current, we can calculate and we can get what we want. So that seems doable. But now, let's try to connect a signal source to the input. For example, a microphone or an antenna or something, right? How would that happen? How would that work? So here's a microphone. Do we have a problem? Yes. We see that this microphone is connected to a short circuit to AC ground. That means that this voltage will never change. This voltage is always equal to supply voltage, regardless of how loudly I speak into the microphone. So that's no good. I have shorted the input to AC ground. All right, so I cannot do that. I am happy with a DC voltage here equal to VDD, but I don't want it to be just a resistor, just a short circuit. So what I'm looking for is some other device that maybe still gives me a DC level equal to VDD, but does not create a short circuit as far as the signal is concerned. So for that, we do it like this. We draw the circuit again, and we use a resistor between this point and VDD. So call this RG. So now you can see that when we have no signals, because the current through the gate is close to 0, the voltage across RG is close to 0, so the voltage at the gate is equal to VDD. So we still have proper bias conditions, but now if the microphone is connected, the microphone is not facing a short circuit, it sees an RG, and if RG is very large, the microphone doesn't see any attenuation. Let's say the microphone internal resistance is 100 ohms, and I pick RG to be 2 kilo ohms. Then 100 ohms and 2 kilo ohms do not attenuate the signal much, so we're happy with that. So that's a very simple method of biasing the source follower so that the signal goes in and comes out, and that's how we can build a circuit. Of course, if you remember, in some cases, this device wants to impose its own DC value. So if you remember, I had this antenna I showed you before, and I said if I try to connect this antenna from here to ground, I create a short circuit from here to ground, like this. And that's not very good. In those cases, I have to place a capacitor between the preceding device or circuit and this point to make sure that the DC level at this point, which is VDD, does not disagree with the DC level of this device or this circuit, right? If that device wants to impose its own DC level. So we always have to be mindful of the preceding device or preceding circuit when we connect them to another amplifier stage. Very well. So that's really all there is to it as far as the biasing of the source follower is concerned. You will see in more advanced courses that oftentimes we prefer to use a current source instead of RS. So what you might see is we use a current source here and a resistor here, with the hope that this current source has a higher impedance than what this RS could do, and as a result the voltage gain from here to here is closer to 1. If you remember, you want RS to be much greater than 1 over GM. And this current source can be realized, as you know, as a single MOSFET, right? So that would be the way we build that current source. But in this course, we don't worry about that too much. In today's series on Frontiers in Electronics, we will be looking at one application of electronics that you probably wear on your hand, on your wrist all the time, and that is the watch, the crystal or the quartz watch. So you might see, if you look at the face of your watch, that says quartz here, and you might wonder what quartz means. So they will look at the internal operation of the watch or clocks that use that type of mechanism as well. The electronics is actually quite interesting, even though it was originally conceived back in late 1960s or early 1970s. In fact, if you can find one of these in a museum, this is how the quartz watch looked back in olden days. Back then we did not have LCD displays, the black display that you see today. Rather, we had LED displays, light emitting diodes. So these are light emitting diodes. And the problem with the LEDs is that they do need a significant current through them to have some light, to produce some light. So back then, actually, you would have to press a button here to light up the display and read it, and then you would let go of the button and the display would become dark again. So most of the time the LEDs were off, you wouldn't see them. Only when you wanted to look, you would have to press and look at your watch and read the time. But what's inside here anyway? When we say it's a quartz watch, what does it mean? So if we look inside, if you open up and look at the back, this is what we see. We have a watch battery. Then we have what we call a crystal. You see this little cylinder here with 2 legs, 2 terminals. This is a quartz crystal. It's a crystal made of quartz. And then we have a little IC here. There's some circuitry inside this chip. And then the result of this guy and this crystal drives a coil. You see this is a coil. It's a wire wound around something, around the core. And this gives certain pulses to the gears inside the watch. So there's a nicer drawing here that you can see better. So here again we have a quartz crystal, and this goes to this, they call it microprocessor, some sort of chip, some sort of circuitry, and then that result drives this coil. This coil activates these gears, these gears turn. They turn the second hand and the minute hand and the hour hand. Okay, that's how it goes. But let's try to focus on this part, the electronics part of this, and see how this works. So it's actually quite interesting. All right, so the way we do this is that we start out with a crystal oscillator, just like an oscillator. We've seen examples of oscillator usage. An oscillator is a circuit that generates a periodic output. So here's an oscillator. This is the symbol for an oscillator. And what it does, it generates a periodic output. It could be a square wave or sine wave or whatever you want. It goes like this. And to this oscillator, we have attached a crystal. Crystal is shown by this symbol. All right. The frequency of this oscillation is given by the resonance frequency of this crystal. And it is equal to the oscillation frequency is equal to 2 to the 15 hertz. All right, it's about 32 kilohertz. Okay, so why do we need a crystal here? Well, you expect your watch to be relatively precise. So for example, let's say you wanted to lose or gain no more than 1 minute in 1 year. So the accuracy that we are dealing with here is very tight. We have about 500,000 minutes per year. So 1 minute over 500,000 is an accuracy of 2 parts per million, right? So the accuracy, delta F, is about 2 ppm, 2 parts per million. So it has to be a very precise oscillation frequency. This has to be this much plus minus 2 ppm, 2 over 1 million, right? And that's why we need a crystal to define that oscillation frequency. Okay, so that's what happens inside this quartz oscillator. This quartz connects to some circuitry here that produces that oscillation. But now what do I do with this? How do I generate what I need for the second and the minute and the hour hands? Well, if I have 2 to the 15 hertz and I give it to a counter, a digital counter that counts. It keeps counting these pulses, and for every 2 to the 15 of those, it generates 1 pulse. Okay? So it generates 1 pulse, and it doesn't generate anything for another 2 to the 15 cycles. So now what this means is that because we have 2 to the 15 pulses per second here, and this counter produces only 1 for every 2 to the 15, these pulses happen 1 per second. So here, from here to here, we have 1 second. So the frequency is 1 hertz. Now that 1 second is good, because that 1 second goes and drives this magnet here, this coil, and this coil activates this gear. So every time there's a pulse, the second hand moves by 1. All right? So this counter counts to the 15. We say it divides the frequency by 2 to the 15. Now that we have a 1 second time base, we can go ahead and create our minute hand. How do we do that? Well, divided by or counted by another factor of 60. So this is another counter, and divides by 60. So the second counter produces 1 pulse every minute. And then we divide by another 60, that gives us the hour. And if you have a calendar, you divide it by 24, etc. You can get all the other numbers. So all of these counters are inside this so-called microprocessor. In olden days, this was not really a microprocessor, but just a few counters. And the enabling technology for all of these was CMOS. Because without CMOS, these would consume too much power. And you could not possibly have a watch run from a little battery and last a long time. With my watch, I change the battery once every, 4 years, 5 years. So that's a very, very small power dissipation for having an oscillator and some counters, etc. So that's the beauty of electronics, even as early as 1970s. Okay, now that we have studied the source follower, let's try to summarize all of the stages that we have learned so that they all are in our minds nice and clean and clear. So let's do a quick summary of these stages. We had the common source stage, so CS, and it looked like this in the simplest case. Or we can use this, replace this resistor with other types of devices. We saw that we can replace it with a current source, like so. Or we can replace it by a diode-connected device, like so. These are all possibilities. We can also degenerate this, the transistor if you want. So I will just draw that as a new color. So we can also have degeneration or not. So we have different possibilities, different combinations of these things. But in any case, we can have degeneration or not, and then the load can be different types of devices. In all of these cases, we said that the voltage gain is equal to minus RD divided by RD plus 1 over GM. And RD, sorry, not RD, RS, if lambda is equal to 0. So we see that RD represents the total resistance we have here. It can be a physical resistor, or it can be the output impedance of a current source, or it can be a diode-connected device. They all become RD. RS represents the total resistance tied between the source and AC ground, and then 1 over GM is that of the transistor. Okay, then in addition to common source, we had the common gate stage. And in this case, the input is applied to the source and taken from the drain. So V in is here, V out is here, and there's a resistance. Again, like the common source stage, we can replace this load with a current source or a diode-connected device. So it doesn't have to be a physical resistor. And we saw that again with lambda equals 0. So let's just say lambda equals 0 for now. We saw that the voltage gain of the circuit was given by GM times the total resistance tied between the drain and AC ground. Okay. What was also interesting was that the input resistance of the circuit was 1 over GM, whereas the input resistance of the circuit was very high. The output resistance of this circuit and this circuit are the same and equal to RD if lambda equals 0. The last stage we studied today was the source follower. And for the source follower, so SF, we have we have something like this. Let's erase this. So the input goes to the gate of the device and comes out of the source of the device. And then we have to have something connected to ground to pass the bias current of the MOSFET. We call that RS. And the voltage gain in this case is less than 1. It's equal to RS divided by RS plus 1 over GM. Also interestingly, the output impedance of the circuit, so if you sit down and look out here, is equal to 1 over GM in parallel with RS. Because looking at the source of the device with the gate grounded, I see 1 over GM. And looking downward, I see RS, and these two are in parallel. So that's the output impedance of the circuit, which is a relatively low value, somewhat similar to the case of a common source stage, common gate stage. All right, so because of its low output impedance, this circuit is capable of driving relatively low impedances, like an antenna or a speaker and that sort of thing. And that's why we thought of this as a buffer. A buffer, a voltage buffer, is one whose input impedance is high and whose output impedance is low. So this is a reasonable approximation of a voltage buffer. And that's why we used it to interface a common source stage with a 50 ohm antenna. All right, so these three form the foundation of many different types of circuits that you will see in the future. There are some other circuit topologies that we will study in courses after this course, but these three are essential to everything that we study in electronics. Very well, our time is up, and I will see you next time.